Swayam Prabha. Digital India. Educated India.
Friends, let us take a pause and summarize what we have done in this what I call as the first module in our reaction engineering course, and this essentially refers to thermodynamics and kinetics. So, what we are going to do today is briefly look at what we have done so far and then look at few problems and solve it and see how to solve such problems. These are typical problems. Of course, one cannot cover up all the problems or all kinds of problems, but these are few representative problems which you may come across in your reaction engineering practice. So, we started our discussion after a brief introduction by looking at how do we represent the reaction, and we said we will define the stoichiometric matrix so that when we have large number of reactions R, let us say, and there are n species participating in these reactions, then how do we represent these reactions. So, we said that we will define the stoichiometric coefficient nu ij as the stoichiometric coefficient of species j in the ith reaction, and then represent the ith reaction as summation nu ij aj equal to 0. And the idea here is that we now can denote whether the the species is a reactant or product by looking at the sign of this stoichiometric coefficient. If it is negative, then we say that it is a reactant. If it is positive, then we say that it is a product. We then moved on to look at how do we measure the progress of reaction, and we defined two quantities here, namely the extent of reaction alpha and the conversion F. The prime difference between these two quantities is that the extent of reaction alpha is tied down to the reaction, whereas the conversion F, or at times we have used notation X also, is tied down to the species. So, if there are R reactions, for example, we will have R extent of reactions alpha 1, alpha 2 and so on, whereas when it comes to conversion, it is tied down to the species. And we cannot define conversion for all species, because if you have started your reaction with non-stoichiometric quantities of reactants and products, then typically there will be one reactant which will be limiting or which will get consumed first, and once it is consumed, reaction cannot proceed further. So, we define the conversion using this what we call stoichiometrically limiting species. We also talked about thermodynamics and chemical reactions. Why thermodynamics is important? First of all, it tells us about the heat changes that accompany a reaction. So, we can calculate the heat of reaction as summation of nu j h j, that is partial molar enthalpies h j, and nu j our stoichiometric coefficient. This tells us, for example, whether heat is going to be liberated in our reaction or heat is going to be absorbed from the reacting system. So, whether we have a exothermic reaction or we have a endothermic reaction. So, the sign of delta H, the heat of reaction, positive endothermic reaction, negative and exothermic reaction. We also talked about the condition of equilibrium, because this is an important quantity, because it tells you how far you can drive your reaction without how far can you drive your reaction at given operating conditions. So, we for example talked about the condition of equilibrium, which we can write as summation mu j equal to 0 for a single reaction, and similar thing summation nu I j mu j equal to 0 for any ith reaction. Nu j as before are our stoichiometric coefficient, and mu j is nothing but our partial molar free energy or the chemical potential. And we spent little bit of time on how we define this chemical potential depending on whether the reaction is a gas phase reaction or a liquid phase reaction or a gas liquid reaction or gas solid reaction and so on. The condition of equilibrium remains the same, but how we define our chemical potential differs when we have different phases. Subsequent to this, we came to the kinetics of the reaction, whether it is a irreversible reaction or whether it is a reversible reaction. So, the idea here is to define the rate of reaction, and the rate of reaction we define saying that in a closed system, there is no exchange of mass with the surrounding. So, like a batch reactor for example. So, in a closed system, the rate of reaction R is given by 1 over V d alpha dt, where V is the volume of the reacting mixture and alpha is the extent of reaction as we had defined earlier. A property of extent of reaction, namely it has a value 0 at the beginning because reaction has not progressed at all, to an upper limit of either 1 or whatever is dictated by the equilibrium of the species. So, the alpha E, that is what we find from our condition of equilibrium. Whatever may be the upper limit, the extent of reaction is always increasing, and at best it can reach a saturation value either when the reactant is completely consumed or the equilibrium is reached, which means that a d alpha dt is always positive, and therefore, we define our intrinsic rate of reaction as a positive quantity. This is again tied down to the reaction. So, the change of species moles or rate of change of species mole R j is related to this R as nu j into alpha. So, for example, if R j is the rate of change of jth species, then we call it equal to nu j into R, nu j into R, that is our reaction rate or intrinsic reaction rate as we have defined. Now, empirically there are several ways of defining reaction rate. So, power law kinetics or law of mass action kinetics, and then there are other forms that one could have, but these are the common forms that are used. We also then summarized our discussion or completed our discussion by looking at ideal reactors, that is what is ideal about them, namely the flow conditions with perfect mixing as in stirred tank reactor, or no mixing in the axial direction or in the direction of the flow as in the plug flow reactor. So, we talked about these flow patterns, then batch and continuous reactors, semi batch reactors, and the idea of residence time, space velocity and so on. Towards the end, we also looked at how we can compare the performance of two reactors, namely stirred tank reactor and plug flow reactor, and came to the conclusion for reactions which follow power law kinetics with power being a positive number, plug flow reactor will always give you better conversions than the same volume, but operated in a stirred reactor manner. But there are situations where stirred reactor will give you better conversions, both isothermal as well as non-isothermal. So, with this brief summary, now let us look at few of the problems that one can encounter, and we will take few typical problems and see how we can solve them. Now, before we go to the actual problem, I want to emphasize that while solving the problem, I have seen tendency of students, the moment they get papers from their examiners, they start writing something. I do not know what they start writing, but they start writing, and I think this is little dangerous, because it is always helpful to look at the paper or look at the question and try to play a game in your mind to figure out what is the question, what is it that I am trying to find out. Often one finds that what appears to be question as written in black and white is not really the question. So, one has to look at, is there any other meaning behind what is the question asked, and I will elaborate on that as we go along. The second thing, that if at all you want to start writing, I think it is always better to write all the information that you have through your problem in a concise manner. That means, what is that data. The third thing that you need to think before start writing is, which tools and knowledge base am I going to use. Does this problem refer to thermodynamics or kinetics or reactor design, isothermal, non-isothermal. So, try starting your solving your problem by organizing your ideas before starting some equation and trying to get something without having a clear idea as to what is the objective. So, let us take our first problem, and it says that it is simple. There are set of reactions given, 6 of them, and we are supposed to find independent number of reactions in the formation of formaldehyde from methanol. So, our main reaction may be methanol decomposition or dehydrogenation to formaldehyde and hydrogen, but there are several reactions that can occur. Now, remember, when we talked about thermodynamics or kinetics or stoichiometry for that matter, we always talked about independent reactions, and therefore, the first step that we need to do in solving any reaction engineering problem is to see whether the set of reactions that are given are independent or not. The moment this question is posed, what comes to mind? How can I find these independent reactions? I can start looking at these reactions and then see whether any combination of any two reaction gives me third reaction and so on. In fact, if you look at this set of reaction, you can after little practice, or if you are smart enough, you will realize that my reaction 3 is actually my reaction 6 minus my reaction 1. So, this is what gives me my reaction 3. So, these are not independent reactions. So, that is one way of solving this problem, but that is possible only when you have few reactions, and even in this case when we have only 6 reactions, although the first one is easy to find, the second one is not that easy. So, what is it that we need to find? What knowledge base do we need to use? We need to use the fact that we can represent these reactions as a stoichiometric matrix, and then look at the rank of this stoichiometric matrix, which gives me what are the independent reactions. So, let us try doing that by write the stoichiometric matrix. So, let us say we start with our first reaction, namely methanol gives formaldehyde plus hydrogen. Now, if you examine this reaction set, you will see that there are 6 reactions. So, let us say that we put reactions over here 1, 2, 3, 4, 5 and 6, and let us start writing the species that are involved in this reaction. So, what are the species that are involved? So, we can see here it is methanol, formaldehyde, hydrogen, oxygen, water, carbon monoxide, carbon dioxide are the species. So, as a column, let us write those species. So, methanol, formaldehyde, hydrogen, oxygen, water, carbon monoxide and carbon dioxide. So, for each reaction one at a time, we are going to represent the stoichiometric coefficients of these species in a given reaction. So, if you look at the first reaction, my methanol is a reactant with a stoichiometric coefficient 1. So, it will be as per my convention -1 because that is a reactant. Formaldehyde being product as +1 and hydrogen also being product as +1, and there are no other species. So, I will write my first entry as -1, 1, 1, 0, 0, 0, 0. If I do the same thing for the second reaction and so on, I will get this particular stoichiometric matrix. That is, all I am doing is I am looking at one reaction at a time and seeing what is the stoichiometric coefficient, putting a minus sign if it is a reactant and putting a plus sign if it is a product. So, this is my stoichiometric matrix nu, and my reactions are mu ij aj equal to 0, or if I represent vector A as A1, A2, A3, An, 7 species here, then this represents my reaction set. So, we will represent this reaction as nu A equal to 0. So, our next task is to find out the number of independent reactions and what those reactions are. Now, just looking at those reactions or looking at this matrix, we said that my reaction 3 is 6 minus 1 is my third reaction, and you can actually do this exercise and you will see that the row 3 is obtained by subtracting respective elements of row 6 and row 1. But that is not an ideal way, because if you have hundreds of reactions, how will you know? So, what is the next thing? I have to find the rank of this matrix, and the rank, it turns out, in this particular case, we can of course use, and there is no reason why we should not use, any available software such as MATLAB, Mathematica or any other program that you yourself have written to find the rank of this matrix. And it turns out the rank of our matrix nu is 4, and we can take any 4 reactions. So, 1, 4, 5, 6, any 4, but we should be careful, and with these are my independent reactions, and then as I said earlier, my reaction 3 is actually 6 minus 1, and my reaction 6, once again reaction 6 is actually 2 times 1 plus 4. So, if I can choose 1, 4, 5, 6 as my independent reactions, I have satisfied the requirement. Sorry, my reaction 2, I stand corrected. My reaction 2 is 2 times reaction 1 plus 4 minus 6. You can go back to that reaction set and see how it works out. So, this is the first problem, simple one. We will go in the order in which we covered various material. Okay. The second problem, let me read out the problem statement to you, and this is also something we require every now and then, even when we are doing reactor design and so on. What is it? It is namely setting up of the stoichiometric table. So, here we have a mixture containing 20% SO2 and 80% air is charged to a flow reactor, in which sulfur dioxide is oxidized to sulfur trioxide at constant temperature and pressure. The reaction is given to us. So, our job is to set up the stoichiometric table for above reaction, and we are also expected to give expressions for concentration of SO2, O2, SO3 in terms of conversion F. We will assume perfect gas behavior. Okay. Now, this is a straightforward problem, except there is a small hitch, namely we have been asked to find the concentration expressions in terms of conversion F. Now, we know that we define conversion in terms of species which is chemically limiting or stoichiometrically limiting. So, our first job here would be to find out among SO2 and O2 which is the species which is stoichiometrically limiting, and unless we do that, setting up of this stoichiometric table does not make any sense, or it will be incorrect if we choose a wrong species, because what will happen if you choose a wrong species is that conversion either will go above 100% or may become a negative value. So, how do we find out which is the limiting species? And to do that, we have been given this particular information. So, what is the information that is available to us? We know that there is 20% SO2 and 80% air in our feed. Okay. So, either you take it as a molar feed or let us take molar feed. So, we say that we suppose our molar feed is 1 mole, which actually is not 1, but it can be anything, but if we take 1 mole as a basis, then we know that there are 0.2 moles of SO2 and 0.8 moles of air, which if we now what is our reactant? Our reactant is not air, it is oxygen. So, air has oxygen and nitrogen. So, which assuming 21% oxygen, I can write this as 0.168 oxygen, and the remaining namely if my mathematics is correct, will be 0.632, it should add up to 0.8 moles of nitrogen. Okay. So, what we have is 0.168 moles of oxygen and 0.2 moles of SO2. So, which is our stoichiometrically limiting species. In this case, what we say, we will go back to our reaction. You know what is the formal way of doing this, that is, look at the ratio of minus Nj0 by nu j and choose the minimum of this value, but it amounts to doing the following. For every mole of oxygen, 1 mole of oxygen, we need 2 moles of SO2. So, if we had 0.168 moles of oxygen, we need double that quantity of SO2 for complete conversion of oxygen. So, that would be, so stoichiometrically for 0.168 we need 0.336 moles of SO2. But how much do we have? We have only 0.2. That means, SO2 is our limiting species, and we should therefore define conversion in terms of these limiting species, namely SO2, and then set up our stoichiometric table. So, let us try to do that by setting up this stoichiometric table, and by recognizing that this is my reaction. So, if I take my species 1 as SO2, species 2 as O2, species 3 as N2, because that is also there, species 4 as SO3. Okay. So, how do we proceed? We say that, let us say, so I will just write here, although there is, okay, let me try writing it here, initial, change and final for all these species, and let us say F naught SO2 is my initial, F naught O2, F naught N2 and F naught SO3 as my initial, and I am going to define my conversion F in terms of SO2. So, let us say the change is F into F SO2 0 is how much has changed. So, final or whatever is remaining is 1 minus F into F naught SO2, that is final is initial plus change. Now, for every F into F naught SO2 that has changed, how much has oxygen changed? Strictly speaking, we need to identify my species. So, I can write here my stoichiometric coefficients nu for each of these species. So, that is -2, -1, 0 and +2. So, how do we set up the stoichiometric table? We say that it is minus nu 2 by nu 1 into F naught of SO2. So, that is how much it has changed. So, if we now substitute what is our nu 1, nu 2, nu 3, nu 4, if you substitute that, I will get here in this particular case, I will get 1 by 2, and therefore, this will be F naught of O2 minus half F naught of SO2, nitrogen is not participating. So, it remains same as before, and for every we use the same formula as we had written. So, this will be minus 2 by minus 2. So, this will be simply F into F naught of SO2. So, this will be F naught of SO3 plus F into F naught of SO2. So, I can now write total here, let us say total. So, this if I say it was F naught, then this will be F naught SO2 plus F naught O2 plus F naught N2 plus F naught SO3, and if I do the same thing over here. So, I am just going to add up. So, minus 1 plus half, and you know what needs to be what needs to be done. We will get F t total, that is the final one, as F naught into 1 minus point, or rather if you take a total, we will get F naught minus F SO2 naught into 0.5 into F, if you add up all these quantities. So, now we have our stoichiometric quantities. So, I can take here F t as F naught minus 1 minus, I am just going to rearrange this, 1 minus F SO2 naught by F naught, which is 0.5 0.2. So, 0.2 into 0.5 into F, and this tells me what is my So, one thing that we see now is that my total moles is no longer constant, because there is change in number of moles in the reaction. From 3 moles on the reactant side, we are getting 2 moles on the product side. So, my flow rate is changing. Okay. So, now let us, what is our objective, what is our question? Our question is to get concentration of SO2 in terms of its conversion. What is concentration? Concentration is the molar flow rate of SO2 divided by the volumetric flow rate V. Okay. So, that is what our concentration is. We know our molar flow rate in terms of, this is my F of SO2. I know that in terms of conversion, but what about volumetric flow rate? Remember, we have a gaseous reaction accompanied by change in number of moles. So, if I have now, or if I make use of my ideal gas behavior, which is, what is that? P into V, volumetric flow rate, is total number of moles RT. So, if I take my pressure and temperature constant, then V by V naught is F t by F naught, which from the above equation, this equation over here is 1 minus 0.1 F. So, now let me put F naught of SO2 into 1 minus F for F of SO2, and for V I will put V naught into 1 minus 0.1 F. These two together now gives us what is F naught of SO2 by V naught? those are all inlet conditions. So, this is nothing but concentration of SO2 at the inlet. So, minus 1 minus F divided by 1 minus 0.1 F, and we can go on doing this for all of them. For example, for concentration of O2, it will be F of O2 divided by V, which will be F naught of O2 minus 0.5 F into F naught of SO2 divided by V naught into 1 minus 0.1 F. Once again, in this particular case, we can take F naught of SO2 out as a common factor and then write this as 0.8 divided by 0.8 into 0.21 divided by 0.2 minus 0.5 F divided by 1 minus 0.1 F. What are all these? On the top is 21% of air, which was 80% of the total feed, which is oxygen, and on the denominator here is 0.2, which is my mole fraction of SO2. So, likewise we can go and complete my kinetic or my concentration expressions. I leave it to you to try out for concentration of nitrogen, concentration of SO3 and so on. Let us move on to the next problem, and the next problem is about calculating the equilibrium conversion. So, what we have been given is, in the production of methane from water gas, the following reactions occur, namely carbon monoxide plus 3 moles of hydrogen giving methane and hydrogen, and hydrogen plus carbon monoxide giving carbon dioxide plus hydrogen. Calculate the, and equilibrium constants are given. Calculate the equilibrium composition for an initial composition of 4 moles of hydrogen per mole of carbon monoxide and reactor pressure of 5 atmosphere. So, here what is the knowledge base that we need to use? We need to use the condition for equilibrium. There are 2 reactions. So, that condition, if I write my species as all ages, my reaction is summation nu 1 j aj equal to 0, and what is my concentration vector? So, A1, A2, A3 and so on. For this case, carbon monoxide, hydrogen, methane, water and carbon dioxide. So, I have my 4 or rather 5 species, 2 reactions. So, this is my first reaction, reaction 1 and reaction 2, which is summation nu 2 j aj equal to 0, for which I have been given equilibrium constant. What is my nu matrix? Stoichiometric coefficient matrix. Again, I will not write species on the top and reactions on the side, but directly write what is it? Minus 1, minus 3, 1, 1, 0, and then second reaction minus 1, plus 1, then 0, minus 1, again plus 1. The first column belongs to carbon monoxide, the second one to hydrogen, third one to methane, fourth one to oxygen and fifth one to carbon dioxide. Okay. So, given this stoichiometric matrix and my reactions and my equilibrium constant, I need to find out equilibrium composition. Okay. So, let us try to find out the equilibrium composition. So, what is it that we are going to use? We are going to use the conditions summation nu 1 j mu j chemical potential equal to 0 for first reaction, same thing for second reaction. There are 6 species. So, chemical potentials of those 6 species. I realize that this is ideal gas. So, I can assume perfect mixture and hence use the appropriate equation which I will appropriate equation and solve for getting that equilibrium composition. What else do we need to do? We need to find this equilibrium composition by finding out to what extent can these reactions go. So, let us say that alpha 1 and alpha 2 are two extent of reactions, and we can write number of moles of species 1, 2, 3, 4 and so on, N1, N2, N3, N4, N5, 5 species. How will we write? For example, our first reaction was CO plus 3H2 giving CH4 plus H2O, and what was our second reaction? Our second reaction was H2O plus CO giving CO2 plus H2. So, if we take N1, that is carbon monoxide, it will be N10 plus stoichiometric coefficient in the first reaction times the extent of first reaction. So, minus 1 times alpha 1 plus stoichiometric coefficient of second reaction into extent. What is general formula did we use? We said that Nj is Nj0 plus summation nu ij alpha I. Okay. So, if you do for each of these reactions, okay. So, N2, N3, N4 all related to alpha 1 and alpha 2. Now, we have been given equilibrium constant Kp1, and being ideal gas, perfect gas mixture, we can write this as partial pressure of methane into partial pressure of water divided by partial pressure of CO into partial pressure of hydrogen raised to 3. Where do we get this? We get this from using this thermodynamic equilibrium condition. I can write this in terms of mole fraction of methane into total pressure multiplied by mole fraction of water into total pressure divided by mole fraction of CO into total pressure, and similarly mole fraction of hydrogen into total pressure raised to 3 cube. So, what do we get? Now, where do we get mole fractions? We have already defined N1, N2, N3 and so on in terms of this alpha 1 and alpha 2. We know Kp1 and Kp2 values. So, I can write the same thing for Kp2, but what will be for example CH4? It will be N CH4 divided by N NCO plus N H2 plus N CH4 plus N H2O, that is number of moles. So, we are getting mole fractions. So, if we put all these things together, we will get one equation. If we look at Kp1, so Kp1 which is 12.46, and we put all these information together, we will get an equation Similarly, we will get another equation Kp2 which is 3.45, which again will be in terms of alpha 2 0.8 minus 3 alpha 1 plus alpha 2 divided by 0.2 minus alpha 1 minus alpha 2 into alpha 1 minus alpha 2. So, we have two equations, two unknowns, non-linear equations, we can solve them, we get alpha 1 as 0.189 and alpha 2 as 0.008, and from that we can calculate the mole fractions. Okay. Let us look at next problem. This says that kinetics of water gas shift reaction on platinum is being studied in a laboratory reactor at 1 atmosphere and 900 K. The reaction is hydrogen plus carbon monoxide, carbon dioxide plus hydrogen. We have been given equilibrium constant at those conditions. There exists a possibility of another reaction involving deposition of coke on catalyst, for which equilibrium constant is also given. Determine either minimum or maximum ratio of reactant moles initially present at which carbon will deposit on the catalyst surface. Assume that no products are initially present. What is the significance of this problem? The significance of this problem is that there is a possibility that carbon may get deposited onto the catalyst. So, we need to conduct these reactions or ensure at the beginning itself that no carbon gets deposited. So, how do we go about solving this particular problem? So, what are our reactions? Our reaction is H2O plus CO giving CO2 plus H2, and what is the second reaction which we do not want? Twice CO plus can give rise to CO2 plus carbon in the solid form. Now, we want to avoid this second reaction. So, let us focus on second reaction. Now, we know free energy change is delta G0 plus RT ln P CO2 by P square CO. So, what is the condition under which reaction will occur? Reaction will occur if delta G is less than 0. Other way around, reaction will not occur if delta G is greater than 0, no reaction. Okay. So, we are looking for this particular. So, we are trying to find out what should be initial pressures, initial partial pressures and so on. So, I can write now delta G, what is my delta G0 is minus RT ln Kp prime. Why am I using prime? Because there is a solid phase. So, we talked about how we can define the chemical potential and reactions. So, that is RT ln P CO2 by P square CO. So, now for this I can further write as right. So, I want this quantity to be greater than 0, that means this bracketed quantity has to be less than 0 or less than 1 rather, sorry, less than 1, then only delta G0 will be positive. So, if I now once again set up the stoichiometric table and so on, I want my Kp prime into partial pressure of CO square divided by partial pressure of CO2 to be less than 1 at the startup. So, I will once again set up the stoichiometric table, make use of Kp1, again Kp1 we know what it is. So, if we do that, we will get in terms of conversion, for example, if we define where my alpha 1 my F is conversion and lambda is initial moles of hydrogen to initial moles of carbon monoxide, which is what I want to find out. So, this has a value 2.31, okay, and this quantity I need to less than 1. So, I have another equation, I can write this as so, this has to be greater than Kp prime. So, if I now solve these two for that is, I know one relationship between F and lambda, I know another relationship, this value is given as 5.69. So, first I can solve it using equal to, and then if I do that I get F equal to 0.563 and lambda equal to 0.89. So, if my lambda is greater, that means initial moles of water to carbon monoxide is greater than 0.89, I will not have this reaction or carbon deposition will not take place. So, various different ways in which thermodynamics can be useful. Let us look at the next problem. You have a plug flow reactor for two reactions, A1 going to A2 and A1 going to A3. The kinetics is given. We know A2 is a desired product which costs, or rather which can bring us 6,000 rupees per gram mole. A3 is undesirable which cost 1500 to dispose. So, not only it is undesirable, but it costs money to get rid of it, and A1 has a value of 1000 rupees per gram mole. Volumetric flow rate is 15 liters per second, while concentration of pure A1 in the feed is also given. What size reactor will give an effluent stream with maximum value? How do we solve this? Now, what will be the maximum value? What will be the value of the product stream? Value of the product stream will be the value, because we can sell A2 minus the cost which is required to dispose A3 and minus the raw material cost. So, if I want to solve this problem, first of all I would need to find out this value. What value do we need to find out? We need to find out 1000, and let us say molar flow rate of species 1 is F1. That is a price I will fetch by selling my desired product A2, or I should minus 1000, that is a cost, plus 6000 into F2 minus 1500 into F3. I want to dispose of which cost money, that is this raw material cost and the selling price of my desired product. How do we do this? We have dF1 dV, which is R1, net rate of conversion of species, which in this particular case, if we take the corresponding rates of two reactions R1 and R2, we can write this as 15 C1 square plus 0.15 C1 dF2 dt as dV as 15 C1 square. So, we are just writing the mole balances for 3 species, okay. Mole balances for 3 species. What else is given to us? It says that the volumetric flow rate is known and the concentration in the feed is known. So, what is my F1 in the feed is concentration in the feed multiplied by my volumetric flow rate, and there are no products in the feed. So, I know what is my, that is 0.00. So, I know what is my F10, this value, F20, F30 all 0, no products in the in the feed. So, I can solve these 3 differential equations 1, 2, 3 with the initial condition that F1 at V equal to 0 is this particular value, and then look at how this function behaves, and wherever we get a 0 maximum value, that is the volume that we should be using. And it turns out for this particular problem, that volume, if you try to solve this equations, is 896 liters. So, these are the few examples that we may encounter. There are many more, but our time is limited. If you open any standard reaction engineering book, you will find problems of this nature and many more, but my point in solving these problems is just to give you a head start. Thank you.